Hey guys, Mr. L back at you with another video, and in this video we're going to talk about the basics of chemical bonding. We're going to talk about the three major kinds of bonds that will form, Lewis symbols in order for us to draw Lewis diagrams. We're going to talk about how ionic compounds form. We're going to talk about how covalent compounds form and whether they're polar or non-polar, as well as we're going to talk about how to identify an ionic versus covalent compound. So let's get into this video. So the first thing we're going to talk about is the idea of three different kinds of bonds that we can form. The first one we're going to talk about is ionic compounds. And the way ionic compounds form is there's a giving and taking of an electron, and therefore you have a full positive or a full negative charge, and these opposite charges attract, and this is called electrostatic interaction. The other kind of compound that we could have is a covalent compound, and covalent compounds meaning together, share electrons. So they covalently share valence electrons to make a bond or a shared region where they share these electrons. And the last kind of bonding is metallic bonding. And we're not going to talk a lot about this in this video. So all you need to know about metallic bonding is that the valence electrons are essentially shared amongst all of the other metal atoms, and you have a sea of electrons that are existing around these different metal atoms. And that's what gives its ability to conduct electricity, as all those valence electrons can be pushed in one direction or the next. So now let's talk about the idea of a Lewis symbol, which is representative of our valence electrons for certain elements. The idea was brought about by a guy named G.N. Lewis, which was an American chemist, and he liked to symbolize valence electrons as dots surrounded by the chemical symbol for whatever element you might have. So if we're talking about something like hydrogen, hydrogen has one valence electron, so we would write down hydrogen symbol, the H. I like to imagine I have a square around my symbol, and we're going to fill dots around the flat parts of that square. So hydrogen's only going to have one dot. Hydrogen's noble gas, or the noble gas that it's going to reach, is helium. So typically the maximum electrons hydrogen can take is just 2 electrons to fill to a full S shell. Once we're talking about other elements above hydrogen, we're going to have the next noble gas. So something like chlorine, its noble gas would be argon, and its valence electrons would be 7. So we have 2 s electrons and 5 p electrons. So we go through and give each flat part 1 dot, and then we go pair 3 of the flat parts, leaving 1 dot empty. So it shows 1 spot available for bonding for chlorine. So this is how we use Lewis diagrams. They're essentially like puzzle pieces that you link together to give a full representation on a two-dimensional surface of what the compound's going to look like. Let's talk about ion formation and ionic bonding in general. And by doing this, let's talk about Lewis diagrams or Lewis symbols. So if we have something like sodium, sodium has 1 dot, it's got 1 valence electron. So sodium is going to easily lose this 1 valence electron because it has low ionization energy. So when sodium loses its 1 valence electron, it's going to become isoelectronic with a noble gas, and that noble gas is going to be neon, 10 electrons. So this is going to be more stable. By doing so, sodium is going to form an overall +1 charge. So its overall full positive charge, it has lost an electron to something else. If we have something like a nonmetal who loves to gain electrons, so chlorine has 7 valence electrons, and it would love to gain 1 electron. It has high electronegativity, high electron affinity. It's going to want to rip that electron away from sodium to form chloride ion. And that's going to be isoelectronic with argon. So when we go to form ionic compounds, there's going to be a giving of valence electrons and a taking of valence electrons from one atom to the next to form overall full positive and negative charges. And then those opposite charges are going to attract each other to form ionic compounds with electrostatic interactions. So there's this cycle that is in many textbooks called the Born-Haber cycle. And the Born-Haber cycle is just an energy diagram which shows us what steps we would need to take in order to eventually get to our ionic compound. Well, we would have solid sodium and chlorine gas. We're going to need to put in energy to sodium to cause it to go into the gas phase. Once everything's into the gas phase, we're going to put in energy to ionize sodium. And then that electron is going to be given or taken to chlorine to form chloride ion. And then eventually you're going to have a huge release of energy by having these oppositely charged ions come together to form the ionic compound. And so therefore, ionic compound formation is typically exothermic, where it gives off heat. So that brings us to our next idea of lattice energy. So lattice energy is the energy required to completely separate a mole of solid ionic compound into its gaseous ionic phase. So we're going to have this solid ionic compound, we're going to put in energy, and those ionic attractions are going to be overcome with the energy, and these are going to separate out into the gas phase and exist as ions. And this is governed by Coulomb's law. And Coulomb's law is energy equals some constant times two charge values divided by some distance. So lattice energy is going to be dependent on two things: the charge of the ions and the size of the ions. So if we're talking about the charge of the ions, the two charge values in Coulomb's law are on top of the equation. Therefore, if we have higher and higher charges, we're going to have more and more energy required to break this ionic interaction, so lattice energy would be higher. So higher charges, higher lattice energy. The other thing would be distance, and distance is at the bottom of this fraction in this equation. So therefore, a bigger and bigger atomic radius is going to be a bigger and bigger distance, which means energy would be dropping further and further. So I always like to think about things in terms of increasing lattice energy. Therefore, smaller atoms have a smaller distance, and they can pack closer together. So smaller atomic radius, higher lattice energy due to them packing closer together. So we can use lattice energy as a relative strength of the ionic interaction between a compound. So if something has a higher lattice energy than another compound, it's going to take more energy to break it apart, so it's going to have higher melting point and higher vaporization point, respectively. So the next kind of bonding we're going to talk about is covalent bonding. And covalent bonding is sharing valence electrons. There's no give and take like ionic compound. They're being shared equally, potentially, or unequally between two atoms and two nuclei. So in order for a covalent bond to form, you're going to have attractions and repulsions between two different atoms. The two nuclei are going to repel. The valence electrons in the nuclei of one and another are going to attract each other, and vice versa, as well as the two electron clouds are going to repel each other. So what's going to have to happen is that the attractions are going to outweigh the repulsions in order for a covalent bond to form. If we're again using our Lewis diagrams, let's see how we would form a hydrogen gas particle, H2 gas, which is the allotropic form of hydrogen. Well, if we had a single hydrogen atom, it would have one valence electron. And like we previously discussed, hydrogen would be happiest having helium's configuration of having two electrons. So if you had one hydrogen with one dot and one hydrogen with another dot, but both could accommodate two electrons in their S shell, then one hydrogen would share one electron with another hydrogen, and they're going to share their electron. So both of them are going to share both of their electrons together, and therefore they're both at a helium configuration, forming a covalent bond of two electrons between the two atoms. This is going to be an overall less energy value than them existing as monoatomic species. If we were to look at something like chlorine, chlorine would have 7 valence electrons, one available spot for bonding. And if we were to have another mirror image of another chlorine with 7 valence electrons, one available for bonding, we would form a bond between the two single electrons to form a covalent bond, but then each chlorine would have 6 sets of electrons. It would have 3 sets of 2 for a total of 6 electrons. These would be called lone pairs. It would have 3 sets of lone pairs, so 3 pairs that belong only to that chlorine atom and they're not being shared. Same with the other chlorine atom. It would have 3 of its own sets of lone pairs for a total of 6 valence electrons that are not shared. And then each electron in the middle between here would be shared for a total of 2 being shared in chlorine. So some compounds may need to have multiple bonds between 2 atoms for them to satisfy reaching an octet or a noble gas configuration. So if we had a compound like carbon dioxide, we'd have 3 puzzle pieces. 2 oxygens with 6 valence electrons, so we'd have 2 unpaired electrons on each oxygen, and then we'd have a central carbon with 4 valence electrons, all open for bonding. Well, if we were to draw only one bond to each carbon atom from an oxygen atom, we would still have 2 dots that haven't been paired on carbon, and we'd only have 6 electrons around carbon. So we're going to need to form a second bond between carbon and oxygen and form a double bond. And therefore, we would have 2, 4, 6, 8 electrons around carbon with 4 total bonds going to carbon. Each oxygen would have 2 sets of lone pair for a total of 4, and 2 bonds for a total of another 4, giving it 8 valence electrons or an octet. Something like diatomic nitrogen would need to take a triple bond, and this is typically the maximum amount of bonds that we see in nature is triple bond. Each nitrogen would have 5 valence electrons, 3 spots available for pairing, so therefore it would share its 3 electrons in back and forth to form a triple bond, and then each nitrogen would have a set of lone pairs, giving it 8 total valence electrons after covalent bonding. So sometimes when we form a covalent bond, we don't have equal sharing, and that's going to be determined based on the last trend that we're going to learn, electronegativity. Electronegativity is the ability for an atom or a molecule to attract electrons from something else. And we just give it kind of arbitrary values, with fluorine being a 4 and fluorine being the highest. So fluorine loves electrons. Nothing else rips electrons from fluorine. Fluorine loves to rip electrons from everything else. So you have to think about this in terms of bullying almost. Fluorine will bully everyone else for their electrons. And then you have weaker elements like cesium or alkali metals that would readily give up their electrons to the stronger electronegative elements. So the top and to the right, fluorine is going to be the most electronegative. So as we go across the period from left to right, electronegativity, or the ability to gain electrons, is bigger. And as we go up a group, it becomes bigger. And this again goes back to the effective nuclear charge and shielding. Higher effective nuclear charge, better ability to gain electrons. Less shielding, better ability to gain electrons. So this is why fluorine loves to rip electrons. So if fluorine is in a compound, say with hydrogen, like hydrofluoric acid, fluorine is going to more readily pull that shared electron pair towards it rather than hydrogen, and you're going to create partial poles. And so these are going to be polar bonds, polar covalent bonds, with fluorine having a partial negative charge and hydrogen having a partial positive charge. So fluorine is pulling the electrons closer to it, exposing the proton and hydrogen out to the other side. So you basically have this kind of magnet interaction where you've got a positive pole and a negative pole with hydrogen and fluorine respectively. So the way you can figure out how polar something is by looking at the periodic table and see how far apart the different elements are from each other. Generally, the further apart they are, the greater the difference in electronegativity. Or you can just look up electronegativity values, subtract, and then you can get a value. And you have 3 typical bins that you put these values in when you go to subtract electronegativity. If you take the 2 elements electronegativity and subtract them, and you get between 0 and 0.3, that's a relatively non-polar compound, so you're not going to have poles on either side. Or it might be slightly polar, but it's going to be overall non-polar. If it's between 0.3 and about 1.7, I would say that this is a polar covalent compound. And then anything greater than 1.7 would fall into the ionic category, where you're having a full taking and a full giving of electrons. The way that we symbolize whether something's polar or not is we put some symbols like lowercase delta with a plus or lowercase delta with a negative. Lowercase delta means partially positive or partially negative. It's not a full charge like an ionic compound. So something like hydrofluoric acid would have partially negative on fluorine and partially positive on hydrogen. We could also show this drawing a vector, and I like to draw mine from plus end to negative end. So you would basically draw a plus end over hydrogen and then draw an arrow going towards negative to show where the negativity is being pulled to. So the last thing we're going to discuss is how you would tell the difference between an ionic compound and a covalent compound. Well, the easy rule is to see if there's a metal in the front. If there's a metal in the front, you most likely have an ionic compound. If you only have nonmetals, you most likely have a covalent compound. There are exceptions to this though, and this doesn't take into the account the many oxidation states of metal. the more and more oxidative states that you have for a metal, you can actually begin to start forming covalent compounds with metal. But I think if you just remember that if you have a metal, it's ionic compound, and if you have nonmetals, it's nonmetal, you should be sufficient with this. The other thing that you could do is, again, take the difference in electronegativity and see which of those three bins that this falls into. The other thing that you could do is just look at the properties of the compound itself. If it's got a really low melting point, this is indicative of a covalent compound because these attractions are weaker than full ion-ion interaction. So therefore, if it had a high melting point, then this is going to be usually an ionic crystal. So if you got a really high melting point crystal, that's going to be in an ionic compound. So there it is, you guys. There's the video on types of bonding, ionic, covalent, and metallic, how we use Lewis symbols to represent this, and how we can tell the difference between ionic and covalent compounds. So if you enjoyed this, if you found it useful, send it to your favorite katydid, send it to your favorite E. coli bacterium, and we'll see you in the next video.